Welcome to part 2 of this video on quantum navigation. I was going to do the whole thing in one go, but it started to snow just for a while, so I've come back here to finish it off. In part 1, we discussed how observing a bunch of atoms can help us calculate how far we've moved from our starting point, and also the direction that we've traveled. If you haven't watched that section yet, I really would recommend checking it out first, as this part will build on those concepts, and it may not make much sense otherwise. Now, after watching part 1, you may have noticed something. Quantum navigation simply is not a standalone system. And to understand why, let's start by talking about quantum navigation and also traditional inertial guidance systems. Both systems face the same challenges. They can measure movement and they can measure direction and acceleration very accurately, but they do need other key pieces of information to work effectively. Without this, they can't help you find out where you are or where you're going. The first bit of information which both quantum navigation and inertial guidance systems need is they need to know where you're starting from. I have mentioned them together as they both operate using inertial forces, which are produced by acceleration. I'm sure you remember Newton's second law of motion from school. And yes, I do know that inertial forces aren't real, but that's a different video. Anyway, imagine you're traveling. You might know the distance and the direction that you've moved, but unless you know your starting point, this information, it doesn't really make any sense. It's like saying, I've walked a mile north without knowing where you started. You may have started in a park or a city or in the middle of a desert or a forest. It's meaningless without context. This problem isn't unique to inertial guidance systems. All navigation systems rely on having an accurate starting point. As an example, let's say that I want to walk to that tree. I can measure the distance that I need to travel, I can take a compass bearing, and I can follow it. And as long as I start from here, I'm going to get to the tree. And at any point along the route, I'll know where I am. But if I start from here, the same route, the same compass bearing and distance, won't get me to the tree. It won't, and if I stop, I won't know where I am. So you need to know where you're setting off from. So how do we find our starting point? Well, there are a few ways to find out where you are, but the one we don't need is GPS, as I think, and I may be wrong about this. One of the main points of developing quantum navigation is so that there's no need to rely on satellite signals. The first one is manual entry. It's the simplest method. Just press some buttons on the system and input your location manually. Basically, you tell the system where you are. And for this, a good old-fashioned map is the best way to find your precise latitude and longitude. Maps may seem outdated, but they are incredibly reliable. The oldest map that I know of, there may be older, is 25,000 years old, and it was found in Pavlov in what is now the Czech Republic. So people have been dead reckoning for a very, very long time. Most places on Earth have been mapped to a high degree of accuracy. So whether you're setting sail from Portsmouth in the UK, or Norfolk in the USA, or even flying out of McMurdo Station in Antarctica. In fact, virtually wherever you are, you could always find an accurate map to determine your starting point. Mind you, I remember when I was younger, I used to go climbing up some big hills. And yes, that may be a British understatement. When you're at over 8,000 meters, are you on a hill or are you on a mountain? In fact, what is the difference between a hill and a mountain? I made a video answering that question, and I'll put the link in the description box. Anyway, on the way up to set up base camp on, I think it was Shishapangma in Tibet, that's over 8,000 meters. And we were using the official maps provided by our wonderful Chinese liaison office. And on the way there, we'd be traversing around 7,000 meter plus mountains, which just weren't on the map. In any other part of the world, they would be the tallest mountain on the continent. But the sensors had just erase them from a map. I don't know why. It's not like you could, it's not like you can hide a mountain. Oh well. The second method, if you'd rather not use a map, you can use triangulation or a resection. This involves identifying fixed reference points and then taking a compass bearing from a number of them. Where the lines cross on a map, that's your location. For closer range measurements, you can use LIDAR. And LIDAR sends out light pulses and measures the time that it takes to bounce back. For longer distances or in bad weather, you can use radar, that works on almost the same way, but it uses radio waves. Both methods, if they're properly calibrated, they can pinpoint your location with an accuracy down to 1 centimeter. You can also triangulate from ground-based transmitters. The third method, obviously for spacecraft and systems operating in space, triangulation works slightly differently. Instead of referencing landmarks, you can use celestial objects like stars or planets or even Earth-based transmitters to determine your position. The point of this is that you can always find your starting location and you don't need to use GPS. The next challenge is keeping track of time and direction. And here I'll assume that you've watched part 1 of this video. And in that, we imagined that we were walking north at 1 mile an hour for 15 minutes. After that time, you traveled 440 yards. There's nothing difficult about that. But what if, for some reason, every 15 minutes, you also change direction by 2 degrees to the east? After 2 hours, you will have walked 8 intervals of 440 yards. So you'd think that you would be, 3,520 meters from the start point. However, because you're curving slightly, your actual position will be different. Let me work this out and I'll come back to you. I used my mobile phone to work all this out. After 2 hours at 1 mile an hour, turning 2 degrees east every 15 minutes, you'll be 427 yards east of your original bearing. And the straight line distance back to your starting point will be 3,508, not 3,520 yards. To get back to where you started, you'd need to walk on a bearing of 353 degrees. Now, this isn't difficult to calculate. I can do it on my mobile phone really, really easily. So a computer will be able to do it much, much quicker. But here we're dealing with direction and a certain amount of time. And this is where accuracy becomes critical. Let's say that your watch is running slow by just 1 second every hour. This tiny error means that instead of turning 2 degrees east every 15 minutes, you'd actually be turning slightly earlier, every 14 minutes, 59.75 seconds. And by the end of the walk, this small difference, it really will affect the total distance traveled and the direction back to your starting point. Okay, a yard or two when you're out walking isn't really going to matter. But imagine you're flying in an aeroplane at 500 miles an hour. A timing error of just 1 second per hour will mean that after a few flights, say over a 2-week period, your navigation system could miscalculate your position by 2 miles. And if you're coming in to land at in an airport in foggy conditions, being 2 miles away from where you think you are, this could be quite serious. And this is where the limitations of current navigation systems become very obvious. If you're not sure how to work out error differences when you're walking or flying, I'll put the calculations in the description box. To prevent aircraft from landing miles away from where they should, we use Inertial Navigation Systems, or just INS. These systems help track an aircraft's position and direction, even in places where GPS signals may be just weak or even unavailable. Inertial navigation systems are different from inertial guidance systems. They work on the same principles, but inertial navigation systems they're designed to give passive information to the system or the person who's in control of the steering. An inertial guidance system is different, as it tends to take control of the steering, and for obvious reasons, they're mainly used by the military. So today, let's just say that I know nothing at all about inertial guidance systems. As you may have guessed from the name, Inertial Navigation Systems, they rely on inertia. Inertia is a really simple concept, but you could write an entire PhD thesis on it. I think some people have. But for today, let's just say that inertia is an object's resistance to change. In other words, things like to stay the way they are, unless something forces them to change. I'll give you an example. If something is sitting still, it won't move unless you apply force by pushing or pulling on it. If something is moving, it will keep moving in the same direction and at the same speed unless some force slows it down or speeds it up or makes it turn, such as wind or gravity or a wall. This resistance to change is a key principle that inertial systems rely on. And while inertia itself can't be measured, as it's not a real force, it's just a property of mass. No, let's not go there today. The effect of inertia can be measured by these inertial navigation systems using tools such as accelerometers. These measure changes in speed or motion along a straight line. There are also gyroscopes, which measure changes in rotation or direction. And by combining the data from these tools, the INS system can calculate where the aircraft is and where it's heading, even if there's no external signals like GPS. There are several other types of gyroscopes, such as a ring laser. What these do is these work by measuring the time that it takes a light pulse to travel around a closed loop in different directions. There are other types, such as fiber optic gyroscopes. These work in similar ways, but they use optical fibers. All types of inertial navigation systems are very accurate, but they aren't perfect. Over time, they accumulate small errors in their measurements, and this is called drift. Drift simply means that the system's calculated position becomes less and less accurate the longer that it operates without external corrections. To fix this, the system periodically needs to update from sources like GPS signals or ground-based beacons or other navigation tools. Without these corrections, these small errors can add up, causing the aircraft to end up off course. We're told that quantum navigation should solve this drifting problem. Quantum sensors are incredibly sensitive, and they can detect tiny changes in motion, orientation, and direction. And they do this, as we've said before, by measuring the behavior of atoms or particles. And they do this in a way that is far more precise than traditional INS. The companies developing quantum navigation systems claim that their technology, especially when combined with a quantum clock, they don't suffer from drift. And while this sounds promising, we'll just have to wait and see if it works in the real world. So is all this new? I don't think so. Basically, it's what people have been doing for thousands of years, which is dead reckoning. But this mix of quantum navigation and quantum clocks will be the most accurate method of navigation until something else replaces it. Have you ever wondered how a quantum clock actually works? What makes it quantum? And how is it different from an atomic clock or even a regular clock? So let's start at the beginning. We know that all clocks require something that ticks or oscillates regularly to measure time. A pendulum swings in a grandfather clock. A spring unwinds to drive the gears in some mechanical clocks. Quartz crystals vibrate inside quartz watches. In atomic and quantum clocks, the ticks come from the oscillation of atoms, which are much faster and much more stable than anything mechanical. Oh, if you're not used to the word oscillation, it just means something that moves and then goes back to where it started. Like a child's swing in a playground. Child sits on it, it swings out and it swings back. Atoms have electrons that jump Is that a good word? Yeah, jump, that'll do. Electrons jump between energy levels when they absorb or emit energy. This jump happens at an extremely precise frequency. You can think about it as it acts like a super accurate metronome. For example, cesium atoms, they oscillate over 9 billion times per second. These oscillations they're so stable that they don't change for billions of years. And by counting them, we can measure time really, really accurately. As I said earlier, quantum navigation uses quantum clocks. But what's the same question? What's the difference between an atomic clock and a quantum clock? Well, there are a few differences, but the main one is the type of atomic transitions that they count. In quantum physics, a transition is when an electron moves from one energy level to another. In atomic clocks, they measure microwave transitions, where electrons move between lower energy levels, and when they do that, they emit microwaves, which are, this is just low frequency electromagnetic waves. A common atom that's used for this is cesium. Quantum clocks use optical transitions. This is where electrons jump between higher energy levels. And when they do, they emit light waves, which is why it's called optical. A common type of atom used in quantum clocks would be strontium. So the thing to take from this is that microwave transitions have a lower frequency, and even though they are extremely accurate, they're not as accurate as optical transitions, which have a higher frequency. And this allows much more precise timekeeping. I'll give you an example of just how precise quantum clocks are. If they're not disturbed, they could keep time to within 1 second from now until the end of the universe. Anyway, that is why they're used in quantum navigation. And this is why the UK Ministry of Defence is testing quantum clocks and quantum navigation on its warships right now. I've said that quantum navigation and inertial guidance systems they're basically the same. That's just my opinion. I would say that the major difference is how they measure acceleration and changes in direction. And that quantum navigation is, I'm going to guess here, millions of times more accurate. But I'm not a physicist. I'm a mountaineer and navigation instructor. So I may be totally wrong about everything I've said. Who knows? I asked at the end of part 1 of the first video, will this stop people getting lost in the hills? No. That is what a map and a compass is for. One day I'll become a real YouTuber with AI graphics and a desk and a big microphone and lots of screens. And I'll have scripts and an auto cue behind the camera. I'll show you what's behind my camera. Hang on, we'll turn it round. So this is what's behind my camera, just more trees. But until I become a real YouTuber, I'll just stand in front of the camera, chat away about anything tenuously linked to navigation, and hopefully people enjoy it. If you've got any comments, please post them in the comments box, especially if I've said anything wrong, because I do like to learn about these things. So thanks for watching. The temperature has dropped dramatically, so it's time for a cup of tea. If I do go to other countries, and I do quite often, I've never seen anybody who's not from the UK who knows how to use these small bits of string which are tied to the tea bag. So, as an added bonus, how amazing is YouTube? I thought I'd show you how to use it. Now, obviously my flask already has tea in it, so you'll have to imagine it's just boiling water. Oh, by the way, over 90% of English people, when they do drink tea, drink either PG Tips, Yorkshire tea, or Tetley. Anyway, put the tea bag into the boiling water and leave it brew for a few minutes. Don't do what I've seen many people do when I'm abroad, and just sit it in the hot water for a few seconds. It takes at least a few minutes for the tea flavour to come out, so leave it, don't rush it. Oh, the same thing applies if you're using loose tea in a teapot. Just leave it. Oh, in that case, when you pour it into the cup, It used to be very important that the milk was put in first, as they were using very thin porcelain cups, which would crack if you put boiling water onto it. But now, you know, we've got thicker cups now, so tea in first or milk in first, it makes no difference. Once the tea is brewed, which it has done now, let's imagine it's been in for a few moments. Take the tea bag out, like this, a teaspoon, put the tea bag onto a teaspoon, and then loop the string around the tea bag. And then pull gently, and that way you can dispose of the tea bag without it dripping all over the place. There you go, a bit of extra information. I'm definitely going to delete this, but first, tea bags, quantum navigation and tea bags. No, I'm not.